Hello, hello, hello. In this episode of What's the Big Idea, we're going to talk about rockets. The episode is called It Is Rocket Science, and it turns out that the ideas about momentum that we've been developing, in particular conservation of momentum, is necessary to explain really how rockets work. And we're going to take advantage of the framework that we've built to really understand some of the most important features that go into designing rockets like this one. This is an artist's conception. NASA's plan is to go to Mars within a decade, send humans to Mars. And this is the kind of rocket that they envision going there. And there are lots of other competing visions of how to get to Mars. SpaceX, Elon Musk's company, is wants to go to Mars. Lots of folks want to get to Mars. So let's understand the basic physics of how you build a rocket to get to Mars. So let's dig in. So, as you know, rockets work by expelling fuel out the back of the nozzle of their exhaust nozzle at high velocity, and they can operate in space. They carry everything that they need to ignite the fuel and expel it out the back of the rocket. And you expel the fuel out, say, to the left in this rocket, and the rocket is going to move to the right. Um, and we're going to consider, just to keep things simple, let's assume that there are no external forces acting on our system here. There's no gravity. We're in deep outer space. And therefore, because it's an isolated system, the total momentum of the system is going to be conserved. So if we keep careful account of the momentum changes, that's going to be our guiding star in figuring out the equations that govern the motion of the rocket. And just a word of warning, one of the things that makes analyzing rockets challenging, and this is something new for us to consider, is the fact that the mass of the rocket is continuously changing. It carries aboard a lot of fuel, and then it's just continuously spewing fuel out the back. So we're going to ultimately have to do some differential calculus in order to solve this problem. But for now, we'll consider a case in which there's one discrete chunk of fuel of quantity of mass delta m, where delta m is a positive number, and delta m is going to be expelled out of the back of the rocket. And the part of the rocket that is not fuel, that's not being expelled, has at this instant in time, at time t, a total mass uppercase M, and we're considering a situation in which the rocket is already traveling to the right at some velocity v. And it's going to, sometime delta t later, the rocket will have expelled this fuel out of the back of the rocket. And as a result, the rocket will now have increased its velocity by some amount delta v. So v plus delta v still points to the right, but it's a slightly longer arrow than it was at time t. And the fuel is going to be traveling at a velocity relative to the rocket of v. The rocket is at v plus delta v, and the fuel is at velocity v plus delta v plus u, where u is by definition the velocity of the expelled fuel, or the so-called exhaust velocity. So u, that's a u. We call that the exhaust velocity, and that's the velocity of the fuel relative to the rocket. That's very important. Relative to the rocket. Okay? Because when you build a rocket, you design the engine in such a way that it expels fuel at a certain well-characterized velocity relative to the rocket. Okay, so we're guided, our North Star here is that the momentum at time t and at time t plus delta t has got to be the same. That's what it means for momentum to be conserved. So now to get things right, we just have to do a careful accounting of the things that contribute to the momentum of the system. So the momentum of the system at time t, which I'll write, whoops, as an uppercase P, at time t, well, The total mass of the system is uppercase M plus delta M, and the rocket at this time, at time t, is moving at a velocity that we've called v. So that's the momentum of the system at time t. Very simple. What about at time t plus delta t? The momentum of the system at time t plus delta t, well, there are now two contributions. So I'll write them as, there's the contribution from the rocket. And the rocket has a mass uppercase M and is traveling at a velocity v plus delta v. So its contribution to the momentum of the system is simply M times v plus delta v. And then the fuel is traveling at a different velocity. So its contribution to the momentum, it has a mass delta M, and its velocity is v plus delta v plus u, where remember u is the velocity of the fuel relative to the rocket. And of course, the direction of u is typically going to be to the left, right? We're typically shooting rockets, shooting the fuel at a velocity which is moving in the direction opposite to the velocity of the rocket. And conservation of momentum requires that this momentum at time t plus delta t is exactly the same as the momentum at time t. So we can equate this thing with this thing and have a true statement. And notice on the right-hand side, there's a term of big M times V, but there's also such a term on the left-hand side. And similarly, there's a term of delta M times V here, but there's also a term of delta V times M here. So we can get rid of those terms just by subtracting them from both sides, and we're left with the following simpler statement. Okay, and to make things even simpler, instead of throwing out discrete chunks, we're going to switch in a minute to taking the limit in which the amount of time delta t becomes small, so the amount of mass expelled during that time becomes small, and the change in velocity that occurs during that time becomes small. And what that means is that when you get a term like this that involves the product of two terms, each of which are becoming small, that sort of term is going to become negligibly small compared to the other terms in the equation, which have only one very small quantity in them. So that's a standard trick, which I hopefully you've seen somewhere in your calculus classes. So in the limit that delta t gets very small, we can ignore this term here. So things have gotten even simpler. And so in the limit that delta t is very small, we can write that m times dv. Now we're changing the delta to a d to indicate that things have gotten really small. That plus dm times u has got to equal 0. And then I'm simply going to divide both sides of this equation by dt to get this equation here. And what's dv dt? That, of course, is simply the acceleration of the rocket. So we have an equation here which we can rearrange to give us what the acceleration of our rocket is, which is really what I was interested in finding. And just rearranging, the acceleration of the rocket is given by 1 over big M times dm dt times u. Okay. Well, that's a lot of symbols. Let's try to make some sense out of them. Okay, so the first reality check is, did we get our signs right? If we expel exhaust out to the left so that u points to the left, which way does the rocket accelerate? Well, if u is a vector pointing to the left, this minus sign ensures that the acceleration of the rocket points to the right, so that's good. And this quantity dm dt here, now dm is by definition a positive quantity, so dm dt is just the rate at which we're expelling mass. So this is DMDT is the rate of mass expulsion, which sounds very nasty, but it really isn't. And what we find is that if you're designing a rocket, it's really important to expel whatever mass you're ejecting, to expel it at a very high rate if you want a big acceleration, which is typically what you want in a rocket. And that is the reason when you look at rockets, one of the reasons why the rocket launches are so spectacular to look at, because they're spewing enormous masses of hot gas out of the nozzle at a very high rate. So the other thing that matters is not only do you have to expel a lot of mass very quickly, but it has to be moving very quickly relative to the rocket. So that's the other thing that makes the rocket launch so exciting to watch, so spectacular. And then, not surprisingly, the acceleration is inversely proportional to the mass of the rocket. So that means well, the good news is, the bad news is that on the launch pad, you're carrying a lot of fuel. The rocket has a lot of mass, and you don't get much acceleration. But the good news is that as you burn off the fuel, the remaining mass decreases, so the acceleration goes up. So right off the lift pad, the rocket may not be accelerating at such a high rate, but as the burn progresses and the rocket has less mass, the accelerations get quite large. So let's look at a real rocket. This is not an artist conception. This is a picture of the SpaceX Falcon Heavy maiden launch just about 2 years ago, February 2018. And this rocket is really a beast. This is the rocket or it's an early prototype of the rocket that SpaceX proposes to use to get to Mars. And when it's sitting on the launch pad, the mass of this rocket is a staggering 1.6 times 10 to the sixth kilograms, 1.6 million kilograms. And the other figure of merit, what really matters in terms of getting the rocket off the ground, is the product of these two terms here. That's known as the thrust. And let's compare some numbers. So first of all, if the mass of the rocket of the Falcon Heavy on the launch pad is 1.6 times 10 to the 6 kilograms, its weight at launch is about 10 times that mg. We'll call it a 1.5 times 10 to the seventh newtons. And the thrust, the product of dmdt times u of the Falcon Heavy uh, at launch is about 2.7 times 10 to the seventh newtons. So the thrust is greater than the weight, which is good because it means the rocket's going to get off the ground. So let's just plug these numbers into our expression for A. Remember, A was derived assuming we were in outer space, there was no gravity. But let's just see what the numbers would be for this rocket if it were being launched in outer space. We take just the thrust, 2.7 times 10 to the seventh newtons, and divide it by the mass of 1.6 times 10 to the sixth kilograms. And you can see we're going to get something like approximately 14 meters per second squared. And if you put it on the ground where there's gravity, you lose 9.8 meters per second squared because of the force of gravity, but you still have an upward acceleration of 4 or so meters per second squared. And remember that as the rocket loses mass, as it's expelling all this mass, the value of that acceleration is going to grow. And in fact, it reaches a peak value during the launch of several several times the acceleration of gravity. I actually have been trying to look up and find the exact number, and I can't seem to find it anywhere on the internet. But I would guess it's something like 3 or 4 G of maximum acceleration. Okay, now if you're going to get a job working for either NASA or SpaceX, there's just one more equation that you really need to know about rockets. This first one here is often called the first rocket equation, the first equation of rocket science. And to become a true rocket scientist, you need to know two equations. So what's the second equation? The second equation lets you calculate how fast the rocket is going to be going when it runs out of fuel. And that's a really important thing, because if you want to get into orbit or reach escape velocity, it's that final velocity that you attain is really important. So it's not hard to derive, although we do have to do an integral, but it'll be fun. So I'm going to start with the first rocket equation, and I'm just going to write it as, well, first of all, I'm going to get rid of the vector symbols because we're going to imagine a one-dimensional world in which the rocket's just going in a straight line. So I don't really have to worry about vectors here. So I can just write this as dv dt is equal to minus 1 over m, big M, times dm dt times u. And now I can multiply both sides by dt, get rid of the dt's, and I have this equation that says the change in velocity is equal to minus 1 over m times dm times u. So in words, what that's saying is, if you want to change the velocity, you're expelling a little bit of mass, and you multiply by u the exhaust velocity, that gives you a big change in velocity. But if you've got a lot of mass on board, that gives you a smaller change in velocity. And again, u is typically a negative number. It's pointing to the left if you want dv to go to the right. Okay, so that's just a general way for calculating changes in velocity for a given amount of mass that's being expelled at a given exhaust velocity. And now to calculate the change in velocity over time, I need to do an integral. So I want to integrate both sides of this equation. And I'm going to start, I'm imagining I'm starting at 0 velocity, and I want to find my final velocity. So on the left-hand side, I'm integrating from an initial value of 0 to a final value. And on the right-hand side, the thing that I'm changing is really the mass of the rocket. We're expelling mass, and the value of big M is going down typically. Now, there's a subtlety here. Um, Remember, this quantity d little m, that was this positive quantity, that was the magnitude of the amount of mass that was being expelled out of the back of the rocket. Um, but when we expel positive mass out of the back of the rocket, the mass of the rocket goes down. So here's what I'm going to do, and don't hit me, but I'm going to change, this is totally legal, I swear. I'm going to change the little m to a big M and change this plus sign, minus sign to a plus sign, because all that we did was that when we expel a positive amount of mass out the back of the rocket, the mass of the rocket goes down. So dm, d big M here is a negative quantity, and that means the overall right-hand side is going to still be a negative quantity, having done that. Okay, why did I do that? So now on the right-hand side, when we do the integral, the variable of integration is the mass of the rocket. So on the right-hand side, the limits of integration are my initial mass of the rocket to the final mass of the rocket. Okay, and on the left-hand side, the integral is very easy to do. The integral of dv is just v, and when I plug in the limits of integration, I get an expression for the final velocity of the rocket. Well, that's great, because that's what we really want to know. And then on the left-hand side, I've got to integrate, well, there's a constant, the exhaust velocity of the rocket is again, this is typically a negative number. U is a negative number. And now I've got to integrate dm over m. And those of you who are paying attention in calculus knows that the integral of dm over m is just the logarithm of m. And my limits of integration are my initial mass and my final mass. So the final velocity is equal to u times the logarithm of the final mass minus the initial mass, and I can write that as the logarithm of the ratio of the final mass to the initial mass. And Again, let's see if we got the signs right. That's the first thing. Is so the final mass is always going to be smaller than the initial mass, which means this we're taking the logarithm of a number that's less than 1. So that the logarithm of a number that's less than 1 is going to be a negative number. And we said that u is a negative number, so we get a positive final velocity. That's good. Okay. Now, if you didn't follow this whole derivation, don't worry. It's not so important. The main thing that I want you to focus on is the result here, because this result is what's known as the second rocket equation. Whoops, let's make it in black. The second rocket equation, because it's a very important equation for a rocket scientist to know. It enables you to calculate the final velocity of the rocket. Okay, so, and again, typically we want very high speeds because we're trying to either get into orbit or escape to Mars. So how do you get a big final speed? Well, the first thing is you choose a fuel that gives you a very high exhaust velocity, and you design the nozzles on your rocket and everything else about the engines on the rocket to maximize the magnitude of this quantity u, the relative exhaust velocity. So that's one thing you can do to get a fast final velocity. But then the other thing that's really important is you want to make this ratio, you want to make this final mass very small compared to the initial mass. Because then when you take then you're taking the logarithm of a number that's small compared to 1, so you get something with a big magnitude. Um, that explains why, at the end of the day, you start off with these enormous rockets, and at the end of the day, the payload is always a lot smaller than what you started with. You've got to expel a lot of fuel to get your payload into orbit. And this also explains why it's advantageous to build rockets in stages, because you really want to make the final mass as small as possible. So once the bottom stage, the first stage of the rocket, once you've used up all the fuel in it, you want to get rid of the casing around it so that you're not carrying that around. You want to make the final mass as small as possible. So anyway, if you know these two rocket equations, that's really a great start to becoming a rocket scientist. And that's it for this episode of What's the Big Idea? Hope to see you again soon. Bye bye.